So right now I want to talk about sets. And sets are a beautiful and complicated subject, and we're not going to do an exhaustive treatment of it, but we're going to kind of get what we need out of it. The suggested exercises are 7, 9, 15, and 33. And for 7, note that for here we have F is proper subset. So if number 7 part F is giving you some issues, just remember that it's talking about a proper subset, and we'll get to that in a moment. So key items for this section: sets, elements, the empty set, subsets, cardinality, power set, and finally Cartesian product. So I'm going to gripe a little bit in advance. I'm not going to give you a great definition of set. So what I'm going to say is a set is an unordered collection of elements. So I haven't really defined set, I haven't really defined elements. I'm going to be relying on your sort of primitive notion of what a set of things is. So a set is a collection of things, and we're going to call those things that we have collected together elements. The big things are that it's unordered. Moreover, we have that it's either in the set or not. So if I have the number 2 in the set, and then I put the number 2 in the set, I still just have one number 2. So those of you that have messed with sets in Python might have some familiarity with this. If an element, call it little a, is in a set, call it big A, we write A is an element of big A. If not, we write A is not an element of big A. Okay? So there are a number of ways that we can define sets. So oftentimes we're going to just define them explicitly. So explicitly, I mean we can write A is equal to 1, 2, 3. So these curly braces say I've got a set, and now when I've written some things in the set, that's what the set consists of. Or by rules, and this has got some name, like by roll or something like that. I can't remember what they call this. Where we write E is defined to be, and I'm doing colon equals, remember I'm defining, X such that X is an even number. Okay, and that's one way to do it. Also, you might see, instead of a colon, you might see a vertical bar here. So that's one way to do it. Or we could just, we could just say E is the set of even numbers, so that there are other ways to do it. So some important sets are the natural numbers, and this is 1, 2, 3, ... We've got the integers, and this is ... -2, -1, 0, 1, 2, ... So this is like the natural numbers as well as their negatives and 0. And then we've got Q, which is the set of rational numbers. R, which is the set of real numbers. And we've also got, C, which is the complex numbers. We're going to kind of avoid that in this class. And finally, we've got this circle with a diagonal line through it, which is nothing. So it's called the empty set. And this is a special set. So the empty set's all over the place. We've also got, you may see open intervals, closed intervals, etc. So A comma B is x such that A is strictly less than x is strictly less than B, and we call this an open interval. We've got square brackets A comma B, and these are, I'm defining these by the way, x such that A less than or equal to x, less than or equal to B, and this is called a closed interval. And similarly, we can do half open intervals, and there's not really a rule with half open or half closed. It's just wherever you have the square bracket, you've got a less than or equal to. Wherever you have the parenthesis, you've got the strict inequality. Half open. It's just, we call these half open. Normal. I hear half open more often than I hear half closed. AB colon equals. So this one, I'll have the strict inequality down below, and then the inclusive inequality up above. Okay. So let's move on. Two sets are said to be equal if they consist of precisely the same elements. So they've all got the same elements. Neither set has one, like an extra one, neither set is missing one, whatever. The set of all elements under consideration is called the universe. So sometimes universe was poorly written, sorry. Even more poorly written than usual. And is often written capital U. Now sometimes we're going to use capital U to just mean whatever set, but if you see a capital U laying around and it's not otherwise given a name or associated to something, then it often means the universe. Moreover, the universe, I said all elements under consideration, that can change from problem to problem. So the universe, sometimes we explicitly define it. We say, like, consider all the integers. Well, then the integers is the universe. Sometimes we just say, consider the people in this room. Or sometimes we just say, consider all the things that aren't odd. Now, if I say consider all the things that aren't odd, that can have a lot of meaning, a lot of different meanings. But if we've been talking about numbers and I say consider all the things that aren't odd, you can probably guess I mean evens. In that case, the integers would be the universe. So sometimes the universe is not explicitly written out, but it's rare that this is a problem. So if you're ever not sure in my class, of course you can ask, but just to say the universe is sometimes not made explicit. Okay, next, if every element of A is also in B, then A is a subset of B. Okay, we write A subset B, and this is, which means that for all A in A is in B. If A is a subset of B, but A is not equal to B, so equal in this sense, then we say A is a proper subset of B. And there are a number of ways to write that. So some people will just write A like subset thing like that. I don't like that notation, okay, because it's a little ambiguous. If I'm ever talking about proper subsets, I'm going to go like this. Okay, that's how I denote proper. The book might use this notation. I'm not sure. I don't have a copy of the book, and I don't know how to quickly get one, so I can't check. But maybe check. But I just personally don't like that notation because sometimes people use this to mean subset that may or may not be proper. Sometimes people use this one to mean subset that is proper. It's not quite a consensus. Okay, so for example, Z is a proper subset of R because every integer is in the reals, but not every real is in the integers. This is a Z. I'm not going to do a whole bunch of stuff with proper and whatnot. Just I don't really see the point in doing a whole lot of stuff with proper subsets. I think, like I said, I think there's one homework problem that deals with it. The big fish that I want to fry is coming up. But before I get there, let me do a couple more definitions, and then I'll do a big, nasty example, and that'll close us out. So if S is a set with exactly n elements, we say the size of S equals n. I guess we write the size of S is equal to n. The cardinality of S is n. So if the size of S is less than infinity, we call S finite. So you'll hear me talking about finite sets and infinite sets. If S is not finite, it is infinite or infinite. Okay. The set of all subsets of a set S is called its power set, denoted script P of S, or quizzically enough, 2 to the S. That's the power set. That's the set of all subsets of a set. Let's do a quick example. Maybe it'll help you see why we use 2 to the S here. Let's compute the power set. Come on. Wow. The power set of the set 1, 2, 3. Nope. Okay, the power set is going to be, well, it's going to be a set, because it's a set, and it's of all subsets. So we've got the empty set. We got the set containing the element 1, the set containing the element 2, and the set containing the element 3. So those are all sets that are subsets of 1, 2, 3. We've got the set containing the elements 1 and 2. We've got the set containing the elements 2 and 3. And we've got the set containing the elements 1 and 3. So these are all subsets. Moreover, these are all proper subsets of the original set. Finally, we've got the whole set itself, 1, 2, 3. And those are all of the subsets of the set 1, 2, 3. Now, this is using script P to denote power set, but also why would I use 2 to the s? So this is a set. This is not a number. This is a set. But as you can imagine, the set containing the elements 1, 2, and 3, and nothing else, is a set of size 3. And 2 to the third power is 1, 2, 3, 4, 5, 6, 7, 8. So just as a side note, for finite sets, the size of 2 to the s is 2 to the size of s. This is just a little side note to help you remember what 2 to the s is. All right, so the last definition I want to give you is the Cartesian product. The Cartesian product of two sets, A and B, is, and I'm just going to define it like this, A little xb, so it kind of looks like times, is defined to be the set of all ordered pairs, so it's A comma B, and I'm just going to add a note here, this is an ordered pair, not an interval. So I know we just used interval notation, that was this A comma B in parentheses. This is a different usage of that. A comma B in parentheses is one of the most common notations, only beaten out in my mind by the vertical bar, which I just avoided by writing colon A comma B, such that A is an element of A and B is an element of B. And I want to do an example of this. So this is, again, this is kind of like the last one. There's no actual multiplication happening, but we will notice, I'll just add a little note here, if A and B are both finite, then the size of A Cartesian product B is equal to the size of A times the size of B. Okay, so that's just a little thing to notice. This looks like a times. Okay, so not a huge deal, but that's something that you might remember. Okay, let's do an example. Let's let A be, let's just compute the Cartesian product. Let's do 2, the set containing the elements 2 and 3, Cartesian product with the set containing the element W, and -1. Okay, solution. I need to look at every possible pair where the first element is on the left is from the first set and the second element is from the second set. So this is going to be, the first pair is going to be 2 comma W. I mean, the order doesn't matter at this point. The order of the pairs doesn't matter, but the order within the pair matters. So for example, W comma 2 is not going to be in this. But 2 coming from the first set, W coming from the second set. Then we've got 2 comma -1, 3 comma W, and finally 3 comma -1. And we notice there were 2 sets of size 2. 2 times 2 is 4. That's not a proof, but hopefully you can see some sort of a pattern here. This is just going to happen. We can do more about that, proving that rigorously later. Okay, the sort of something that you may have seen before. You may have seen like the XY plane called R2, and that's because it's R cross R. And, you know, the elements X comma Y, those are like, you know, X coordinate, Y coordinate. These are where we get coordinates. This is a Cartesian product. That's why we call it the Cartesian coordinate plane, again named for Rene Descartes, who, according to lore, during a fever dream, saw a fly walking on his ceiling and said, "You know what? I think I could determine the location of that just with, you know, anywhere on my ceiling with just 2 numbers measuring the horizontal and vertical distance." And who knows if that's true or not? But that's the sort of story. Okay, so here's the big example. That's what we're going to finish with. But in order to get to the big example, I'm gonna do a warm-up with a little example. So let's let T denote the set of NFL teams. I guess I'll just write set of NFL teams. And we're gonna let P denote the set of Chiefs players. So let's let X be an element, which is Mahomes. Okay, now X is an element of P. P is an element of T. But X is not an element of T. Okay, so X is a player, Mahomes is a player, so he's in the set of Chiefs players. The Chiefs is a team, so it's in the set of teams, but Mahomes is not himself an entire team. And then we can chuckle and say, well, he carried the team. Like, well, I don't think he carried the team. I think he is a great player, and I think the team rose to the challenge and played well with him. But that's just to give you an idea. So now here's the big nasty example, and this is the one that I think you're going to need to spend a little bit of time with. Let's define A to be the set containing the element 1. Let's define B to be the set containing the elements 1 and 2. Let's define C to be the set containing the element 1 and the element 2. And let's let D be the set containing the elements 1, 2, and the set containing the element 1. So this is where we have lots of problems with the rough definition of set that I gave us. So I didn't really give us a full definition of set because, well, number one, it was a bit unclear and circular. But number two, when we have sets that can have elements that are themselves sets, then we open the door to possibilities like sets that contain themselves. And then so the classic paradox is let S be the set of sets that don't contain themselves. So if S contains itself, then it's not in the set S, which means it must be in the set S. So this is a paradox. It's akin to this sentence is false from the propositions thing. I think this is called Russell's paradox. It's also the barber of Seville. The barber of Seville shaves everyone who does not shave themselves. Then who shaves the barber of Seville? Anyway, so we're inviting this when we start doing sets that can contain sets. In particular, sets that can contain themselves. So let's do some examples with this. So here's a list of facts. So A is a subset of B because every element in A is an element of B. A is not an element of B because we don't see the set containing the element 1 listed here. We see the element inside that set, but we don't see the whole set listed here. A is not a subset of C because the element 1 is not by itself in C. There's a set containing the element 1, but the element 1 itself is not in C. Now, A is an element of C because this whole set is listed somewhere in C. Finally, A is a subset of D and A is an element of D, and that's because all of the elements in A are listed in D, and the whole set A, that is just the set containing element 1, is listed in D. B is not a subset of C because we have here B has the element 1, which is not in C. And you might say, I can see there's a 1 right there. No, this is not a 1. This is the set containing the element 1. So remember, this is the difference between, Mahomes being on the set of players, but Mahomes not being in the set of NFL teams. So there's a scope issue here. Again, people, when you're struggling with this, if you've messed with pointers before or dereferencing operators in programming languages, this can really help thinking about this. B, moreover, is not an element of C because I don't have the set containing the elements 1 and 2 listed inside of C. There's a mosquito. Dang it, if I wasn't recording a video, I would have awkwardly swatted at the mosquito and missed, perhaps, breaking something. Now the mosquito is probably going to bite me. Anyways, then B, not doing a good job here. B is a subset of D because every element in B is an element of D, but B is not an element of D. Okay, and let's finish with C is a subset of D because every element in C is listed somewhere in D, but C is not an element of D. I suggest you spend a little bit of time going back over that, and have a good evening.